So this notion is well defined because any two representations have either even number of transpositions or odd number of transpositions. So now let us observe that even permutations have an interesting property. So before that, let me quickly give you an example. So you have let's take S3, consider actually let's take 1 2 3 2. So this is in S3, right? You can immediately conclude that sigma is even because it is a product of two transpositions, right? As we said in the theorem, it is possible that it is also some other, maybe it is a product of some other number of transpositions, but they must also have even number. So sigma is even. On the other hand, another example is any transposition is odd, right? Because if you take 1 2, it requires exactly one transposition, so it must be odd. What about a 3 cycle? I claim a 3 cycle is even. Why is this? So for example, if you take 1 2 3, right? Let us try to write this as a product of 2 cycles, and we saw this yesterday. It is same as 1 2 times 2 3. Is this right? 2 goes to 3, so 2 goes to 3, 3 goes to 2, 2 goes to 1, so 3 goes to 1, and 1 goes to 2. So this implies 1 2 3 is even. Of course, this is true for any 3 cycle. More generally, a k cycle is even if k is odd, and it is odd if k is even. So this is a confusing situation, but it is clear, right? We saw earlier that a 2 cycle is odd because 2 cycle is transposition. A 3 cycle is even. Okay, 3 is odd, but 3 cycle is even. Why is this? Because if you take a k cycle, and we have written this as a product of transpositions earlier, and this turns out to be I1 I2 I2 I3 Ik minus 1 Ik, right? And again, let me repeat once more that if you have one representation as a product of transpositions, that will allow you to determine whether the permutation is even or odd, because every other permutation must have the same number, same parity. The number of permutations must have same parity. Now, how many transpositions are there? There are k minus 1 transpositions here, right? Because 1 2 up to k minus 1. So this tells me that if k is odd, implies k minus, so this is sigma. If k is odd, k minus 1 is even, implies sigma is even, because it requires k minus 1 transpositions. Of course, this is if and only if, or we can write it like this: k is even means k minus 1 is odd, so sigma is odd. So a k cycle has k cycle is odd precisely when k is even. So we can define now, just sometimes it's useful to talk of sign of a permutation. So sign of sigma is either 1 if sigma is even, minus 1 if sigma is odd. Okay, so this is the sign of sigma. So sign is just 1 if it's even, minus 1 if it is odd. Now let's come back to even permutations and look at them a bit more carefully. So we want to prove a proposition, product of two even permutations is even. Inverse of an even permutation is even. So if you take a couple of even permutations and take their product, it's even. If you take an even permutation and take its inverse, that's also even. Why is this? If sigma and sigma 2 are even, that means sigma 1 can be written as a product of tau 1 up to tau r, right, tau k, where k is even. Similarly, tau 2, sigma 2 can be written as some rho 1 up to rho t, where t is even. What is sigma 1, sigma 2 now? This is tau 1 up to tau k, rho 1 up to rho t, right? This is a product of transpositions. So if k and t are even, then k plus t is even, right? That's all we need. If k and t are even, k plus t is even. This implies sigma 1, sigma 2 is even. Because the product decomposition of sigma 1, sigma 2 requires an even number of permutations. This is even, this is even. Now on the other hand, if sigma is even and say sigma is sigma 1 up to sigma k, so k is even. What is sigma inverse? I claim sigma inverse is sigma k inverse, sigma k minus 1 inverse up to sigma 2 inverse to sigma 1 inverse, right? This is clear because in general, in any group, recall, in any group G, A B inverse is B inverse A inverse. So sigma 1 to sigma k whole inverse is, you take the inverses and multiply in the reverse order, sigma k inverse, sigma k 1 inverse. But now if sigma 1 is a 2 cycle, sigma 1 inverse is actually sigma 1, because remember 1 2 times 1 2 for example is E. So this is sigma k minus 1, sigma 2, sigma 1. So these are all transpositions, and sigma inverse is also even because it requires again k many transpositions, which is even. So sigma 1 inverse is even, right? So if you have a product of two even permutations, it's even. Inverse of an even permutation is even. So this is the proof of the proposition. So now let us define a subset An. These are sigma in Sn, sigma is even. So this is the subset consisting of even permutations, right? I am taking all the even permutations. By the proposition, okay, so actually almost by the proposition, An is a subgroup of, let's see, what is a subgroup of a group? It must include the identity element. So that I didn't write it in the proposition, but I should say it now. Certainly, what is the identity permutation? It is even, right? Because it requires 0 transpositions. So this is 0 transpositions. We don't need any transposition to write it. So identity is certainly even, okay, right? So if you think about it, identity is certainly even. And if you take two elements of An, the product is again in An. That was the proposition. If two permutations are even, the product is even. If you take something in An, its inverse is also in An because it's even. So An is called the the alternating group and it's a subgroup of Sn. Okay, now let me just quickly mention one fact about An, and namely what is its order. So now I'm going to introduce a homomorphism. Consider the group homomorphism from phi from Sn to 1 minus 1. So before I tell you what phi is, just a word about what is 1 minus 1. 1 minus 1 is a group, right? This is a group under multiplication. So if you wish, this is a subgroup of non-zero rational numbers under multiplication if you wish, but abstractly it is a cyclic group of order 2. Okay, so what is the group homomorphism phi? I will define phi of C sigma to be sine of sigma. Okay, so if sigma is odd, it goes to minus 1. If sigma is even, it goes to 1. So first of all, phi is a group homomorphism. Right? This is because phi is a group homomorphism because of the proposition that we just did above. Right? Because if phi of sigma 1 sigma, so almost by the proposition, actually we need to be careful. So what is sigma 1 sigma 2? So this is sine of sigma 1 sigma 2, right? Which is another way of saying you write sigma 1 as a product of transpositions and see how many there are. If it's odd, sine is minus 1. If it's even, sine is 1. But by the same idea that we used in the proposition, we can first write sigma 1 as a product of transpositions and then write sigma 2 as a product of transpositions, put them together. If sigma 1 is, I think I used tau 1 tau k, sigma 2 is rho 1 rho t, then sigma 1 sigma 2 was right. Now if k is odd, t is odd, kt are both odd, let's first start with kt even, then k plus t is even. Kt are both odd, then k plus t is even, right? Two odd numbers add up to even number. One odd, one even, right? Exactly one of the two numbers k and t is odd, the other is even, then k plus t is odd. This is the proof of this, because sine of sigma 1 is determined by whether k is odd or even. Sine of sigma 2 is determined by whether t is odd or even. So in this case you have sine sigma 1 and sine sigma 2 are both 1 and the product is also 1. In this case we have sine of sigma 1 and sine of sigma 2 are both minus 1. So minus 1 times minus 1 is 1, which is the sine of sigma 1 sigma 2, because sigma 1 sigma 2 is even, and here 1 is even, 1 is odd, so it is 1 times minus 1, which is minus 1. Okay, so phi is a group homomorphism. I am going fast here maybe, but I hope this is clear enough. So phi is a group homomorphism. What are other properties of phi? So phi is onto, right? Because certainly because Sn contains even permutations as well as odd permutations, right? Because it contains both even and odd permutations, clearly it's on 2. Some even things, for example, 2 cycles are odd, 3 cycles are even. And let's take, so here I am taking n at least, so I am going to, let's say n is at least, in all these considerations n is at least 2. If I take n equal to 1, it's not interesting. So always assume because if you take n equal to 1, then there is only one permutation that's even. So now I claim that kernel of phi, what is kernel of phi? These are things that go to the identity element of 1 comma minus 1. What is identity element of 1 comma minus 1? It is 1. So all permutations is go to 1. In other words, all permutations that are even. So this is precisely an, right? Kernel of phi is an. This is because an is precisely the set of even permutations. Now the first isomorphism theorem says Sn minus modulo an is isomorphic to 1 and minus 1. So in particular, from the counting formula, says that cardinality of Sn is equal to cardinality of an times cardinality of this group, which is 2. Okay, and we know this is n factorial. So we have n factorial equals 2 times cardinality of an. So this implies cardinality of an is n factorial by 2. So upshot of this is exactly half of the elements of Sn are even, the other half are odd. So of the n factorial many elements of Sn, half are even, half are odd, and even permutations are nice because they form a group. So now it is just a quick check for you. Can you also take odd permutations and see if they form a group? So the quick question for you: do odd permutations also form a group? The answer to this is an obvious no, for several reasons. First, identity is not there, right? Because identity is even, so identity is not odd. This is one reason. That's good enough to conclude that they are not a group. But also remember, if you take 1, 2 and 3, 4 are both odd, but the product is even. So this amounts to saying that sum of 2 odd numbers is even. So just like even numbers in integers form a subgroup but not odd integers, similarly even permutations form a subgroup but odd permutations do not. Okay, so this is the end of my video about symmetric groups. So just to recap, what we have done is we have learned how to use cycle notation for permutations. We learned how to write a given permutation as a product of disjoint cycles. Using that, we can figure out the order. Order of a k cycle is k, and order of a product of disjoint cycles is the LCM of the orders of those disjoint cycles. Then we also saw that any permutation can be written as a product of transpositions, not necessarily disjoint and not necessarily unique, but we proved a big theorem saying that the number of transpositions required is always even or always odd. Using this, we have defined the notion of odd and even permutations, and we saw that even permutations form a subgroup of the symmetric group. We call it the alternating group an, and we finally saw that order of an is exactly half of the order of n Sn. So an has order n factorial divided by 2. That means of the n factorial permutations in Sn, exactly half are even, the other half are odd. Thank you.